Today I'm going to explain how to build logic gates. But before that, I'll be using this online visualizer here to explain how this works. The breadboard is the main thing we will be building on. It has two parts, the top and the bottom parts, where we connect our power supply, and the middle part where we'll build our gates. There are two strips going through the top part, a positive strip and a negative strip. You connect the positive to the positive and a negative to the negative. I think this is obvious. In our breadboard, the middle portions are split, which means that only one half of the breadboard receives power at a time. If we want to send electricity to the other side, we have to connect them using a wire. The most important thing to know about the middle part is that these holes where we insert our components are connected vertically. Let me show it with an example. As you can see here, our LED lights up despite the top and bottom wires not being physically connected, as underneath the breadboard they are actually connected. To connect the electricity, we use wires transport electricity, and they aren't very complicated. We can use this electricity to light up and the LED, or the light emitting diode, is the main way of visualizing if our logic gates have worked or not. They have two sides, the long one which receives electricity, and the short one that returns to ground. As you might know, in conventional current, electricity flows from positive to negative, otherwise known as ground. If it isn't connected to ground, the LED doesn't light up. Now you can't connect the wire directly to the power supply using wires, because what will happen is to connect an LED to electricity without blowing it up, we need to use a The resistor is simple. It limits the voltage that it receives enough where we don't explode, destroy, decimate, annihilate, demolish, devastate, wreck, vaporize, dismantle, obliterate, or pulverize our LED. We can connect the resistors to the LED directly, or we can send it to a wire, which then connects to an LED. We don't have to send electricity to the LED though, we can also send it to Now, this is important. Transistors are the building blocks for modern electronics. Usually they're a lot smaller than what we have here, and by smaller I mean microscopic. There are billions of them in your phone. Now our transistor is an NPN transistor. We also have a PNP transistors, but they aren't really necessary right now. They are called NPN transistors because they have two N-type materials with a P-type material sandwiched in between them. What are NP-type materials? I don't know. I didn't do research because I didn't think it was necessary. What I know is our NPN transistors, which I will refer to as just transistors from now on for simplicity's sake, has three parts: a collector, a base, and an emitter. The collector receives current and sends it to the emitter for it to send it wherever it wants. But to be able to send this electricity, we have to send current to the base. Think of the base as a door and our current as the key. When we send electricity, the door opens and the collector can send electricity to the emitter. That's cool and all, but right now we don't have an elegant way of controlling voltage. I mean, we could yank a wire out to stop electricity, but it takes too much effort to pull out a 10-gram wire out of a hole. And then we have to put it back in, and it's too much effort. What we need is a Compared to the transistor, the push button is very simple. When you push the button, it allows electricity to go through it. It is worth noting that if you connect a wire from the bottom left, you have to have it go to the top right, and vice versa. To get this power, we need a... The power supply is also simple. It connects to the breadboard, positive to positive, negative to negative. The power supply can vary, whether it be a battery or this weird thing. Those are all the components. Using these, I've built a simple switch to demonstrate all of them in action. As you can see, originally the LED wasn't lit up, but when we click this button, the base gets voltage and the collector can send electricity to the emitter, which connects to the LED, causing it to light up. Now that we have, hopefully, understood our concepts, we can build our logic gates, starting with the NOT gate.
Today is my 18th birthday,
No, it's not your birthday.
said the no birthday man.
Here's the NOT gate truth table. You can see it's very simple. It takes an input and it basically reverses it. Here's the circuit in the simulator. I'll use the simulator as it's not easy to explain the gates on a breadboard with 50-meter long wires sticking out of it. Here's the breadboard. As you can see, at first the LED lights up, but when I click the button, it turns off. The reason this happens is because when I don't click the button, the only option for the electricity to go to is to the LED. When I click the button, electricity goes to the base of the transistor and activates, and the collector can send voltage to the emitter, which is connected to ground. Now this creates a short circuit, and for some physics reason I don't want to explain right now, the electricity likes to go to ground through the transistor rather than the LED. So the electricity goes to the ground and not the LED, which turns it off. Here's the building process, and here it is in action. I'll now need to explain the AND gate, as it is required to build a NAND gate. Here's the AND gate truth table. As you can see, it has to receive two 1 inputs to work. Here's the gate in the simulator. Now the wire in the top left is connected to 2 wires. Unlike the NOT gate, instead of the electricity going to the LED and us diverting it to a transistor to turn off the LED, the electricity goes to the first transistor from the left, which is powered by the second resistor from the top. Now we need to make it so that the resistor doesn't send current to the base to turn it on. As we saw in the NOT gate, electricity prefers going through the transistor to ground. So we use the same principle here. We use two transistors where the emitter of one of them is connected to the collector of the other, leading to ground at the end. When we turn on both transistors, the second resistor from the top sends voltage to ground, thus not turning on the rightmost transistor, which makes it so that the first resistor can only send electricity to the LED, turning it on. This only happens when both the buttons are pressed, just like how our AND gate suggests that this would happen. Here is the building of the AND gate and its execution. From this point onwards, the NAND gate isn't that complicated. If you look at the truth table, you can see that the NAND gate truth table is just the AND gate truth table inverted. To simulate this effect, we connect our output from our AND gate, which is this wire, to the input of the NOT gate. The only thing to keep in mind here is for this to work, both breadboards must share the same power supply. Here it is in execution.
Turns on, turns off.
Is the rarest ore in Minecraft Deep Slate Coal or Deep Slate Emerald? Both of these have been called the rarest ore in the game.
The OR gate is the final logic gate we will be building. Here's the truth table. As you can see, it turns on when we receive at least a single one input. The circuit is here. You can see that the right side of the circuit is almost the same. The difference is that the resistor that diverts electricity away from the LED is connected to two unconnected transistors separately. This means that only one of the transistors needs to receive electricity from the base. After this, it's just like the AND gate, where the leftmost resistor can't send electricity to the transistor, so it has to send it to the LED instead. Here's the building process and the gate in action.
Okay, this works. And now if I click both, it also works. So, our gate.
So those are the gates. I hope you enjoyed this. Bye.